Okay, finishing up the dot product. One of the applications for using the dot product is work. And it says here you may have been taught that the work done on an object is the product of force times distance, and it is. It's not exactly accurate. Work is actually the product of the distance and the component of force in the direction of motion. So what do we mean by that? So if we take, here's our little stick figure person. This stick figure person is going to push a box. Okay, and we're going to push the box along the floor. If they push the box, and unless they bend over and push the box really, really low on this thing, most people are going to push the box from someplace right around there. If you think about it, if you push a box from the upper corner of the box, the force that you're actually applying looks something like it would be in this direction. So your force would actually be going not only away from you, but also down and into the ground. So you would have a force which is in that general direction. The force itself has two different components to it. One of the components of the force is horizontal. One of the components of the force is vertical. In order for you to actually calculate the work done on the force, the work done is only in the horizontal direction. And if you think about that, this really makes sense, because is the box going into the ground at all? It's sliding along the ground as you push it, but it's not actually vertically changing distance. It's not going down under the ground. Obviously, we're assuming that the ground is going to hold up to the point where that can't happen. So the work done on this is actually in the direction of motion. The motion is the box is going to go this direction. So the motion of the box is horizontal. Well, there's an angle here in between the horizontal and the actual direction that the force is. And the work done is going to be based upon what the force is going to be in the horizontal direction. Well, this would be like, and I don't care what we call it, I'm going to call this A, I guess. So the cosine of the angle in between the work done and the force, well, cosine is adjacent over hypotenuse, so that would be work over, it has to be the magnitude of the force. Therefore, if I actually want to solve for the work done, I'm just going to multiply both sides of that by the magnitude of the force. And if you really think about it, cosine usually goes with x anyway, right? So the cosine in this case is going to give us our horizontal distance. Yay, nice LinkedIn thing there. So the work done is going to be the magnitude of the force times the cosine of theta. So work, which still is a force times distance, is going to end up being the magnitude of the distance, because it's got to be a positive distance, times the magnitude of the force times the cosine of theta. So there is your equation for work done. And ultimately what you want to remember is that this direction, the negative direction, which is down is what I was trying to say, there is no work done because there's no motion in that direction. It's not actually physically going down. the force is going into the ground, but the object itself is not moving in that direction. So there is no motion in that direction. So the work done is only based on the direction of motion. And if hopefully you guys recognize that that magnitude D, magnitude F cosine of theta is the same as D dot F. So really this is just going to depend on which of these pieces of information you're given as far as which of these two equations you're going to use. Neither one of them are very difficult to use though. So let's go ahead and take a look. Alright, let's find the work done by pulling a sled 25 meters if the handle makes an angle of 38 degrees with the ground and a constant force of 12 newtons is applied. So if we kind of just drew a really basic sketch of that, you've got something moving along the ground, and according to this, which is our distance, is 25 meters. And I've got some kind of a force being applied on this thing, and it's making, so you know, you're pulling the sled, you probably got like a handle or a string or something like that, and that makes an angle of 30 degrees with the ground. So my force is given to us as 12 newtons. So we are actually given the magnitude of the distance, because that's just the distance 25, the magnitude of the force, which is 12 newtons, and we're given the angle in between. So it really makes sense, in this case, to use magnitude F, magnitude D, cosine theta. That'll give us our work done. So in this case, magnitude F is 12 newtons. The distance is 25 meters. Oops. And the angle itself was 30 degrees, so cosine of 30 degrees equals the work done. So 12 times 25 is, why is my brain not functioning? 300 Newton meters times cosine of 30, which is root 3 over 2. And a Newton meter is the way you say a joule, for those of you guys who don't know that term. Newton meters are joules. So 300 times root 3 over 2 is going to give us 150 root 3 joules of work done. Now, to mathematicians that might mean something, but to most other people that's not going to mean anything. And in case you didn't already catch it, I have made a mistake and I apologize. I did not read very carefully. This is not 30 degrees, it is 38 degrees. So let's fix that. And that is going to make a big difference because now it's not a unit circle value. So I am going to have to take that out and write cosine of 38 degrees. And this is not something I can figure out without, so I'm going to have to plug that to a calculator and get, a second, 236.4 joules or so. That's the amount of work done to pull that sled over a 25 meter distance. All right, last one. Find the work done for moving a particle from one point 025 to another point 317 by using the force vector 2I plus 6j minus 7k. So again, this is a really simple one because in this case, I'm going to be given enough information. I can just do d dot f. The distance I can figure out in vector form by simply creating a vector from 025 to 317. So the distance vector is going to be 3, negative 1, 2. And I'm going to dot that with the force vector 2, 6, negative 7. So my work done is going to be the dot product, which is 6 minus 6 minus 14. So we get negative 14 joules. And that's it. Just under 10 minutes, like I said, we are good.